Hello. All right. Hello and welcome to tonight's version of Space Drafts. This is Space Drafts number 107. My name is Nick Schragle. I am a fourth-year graduate student at the University of Arizona, and I will be your MC for tonight. For those of you who are new to Space Drafts, welcome. This is Tucson's version of Astronomy on Tap. Astronomy on Tap, by the way, is a network of events for sharing astronomy with you, the public, all over the world in bars and pubs. So if you're elsewhere in the world, you can also look up to see if there's an Astronomy on Tap event near you. How our show works here in Tucson, we have two 25-ish minute talks. In between those, we'll have a 20-minute intermission for you to go and refresh your drinks. And in each of those talks, we will have one trivia question, which is your opportunity to win a little piece of our merchandise. If you are the successful answerer of that question, you can come over to our merch table here and grab that free piece of merchandise. If you aren't that successful question answerer, you can still come over here and grab some merch for yourself. We do only accept cash. Unfortunately, we cannot accept cards, so if you don't have your cash today, come back next month and get some merch. Let's see. One other thing, we do accept donations, so if you want to donate a little bit of money to us to help keep this running as smoothly as possible, that would be much appreciated. One final thing before we get started, as you saw just before we began, there was a train running past Borderlands, and it is tradition here at Space Drafts that every time we have a train come through and interrupt our speaker, what do we do, folks? We raise our glass and we toast the train with a hearty choo-choo. So, without further ado, I would like to introduce our first speaker of this evening. Here to talk about eclipsing binary stars and how they relate to the dark night, please welcome Steward Observatory postdoc, Dr. Koushik Sen.
Hi, I'm Koushik. I started working here at Steward in January, and today I get the opportunity to talk to you about two of my favorite topics, one related to my research, eclipsing binaries, and one related to my favorite superhero, Batman. So, there are no prizes for guessing. My trivia question would be to all of you, what's the relation between Batman and eclipsing binaries? There is a hint. Okay, the story goes something like this. Around 3,200 years ago, Egyptian astronomers looked up into the night sky, which they called heavens back then, and which they thought was a static universe above Earth. And what they found was one of those static objects was changing its brightness sometimes. So their idea of a static heaven was shattered, and they thought that it's like a very bad omen for Earth. The heavens are breaking loose, Earth will get destroyed, and they called that object that was changing its brightness Al-Ghul, or the head of the demon. And this is where the link between Batman and eclipsing binaries comes from. So Ra's Al Ghul is also called the head of the demon, and the first eclipsing binary that was discovered is called Algol, and it derives its name from the term Al Ghul. So this is the history of the first eclipsing binary ever studied in astronomy, and it goes back all the way more than 3,000 years. Okay, I think this demon is not coming up, but yeah. Now, the history of Algol in modern astronomy also has a lot of study done. It was one of the first studied systems in modern astronomy, and in the background is the Harvard College Observatory, where the first spectra of this system was taken. And the first recorded variations in the light coming from Algol was in the 1600s, where Montgomery recorded the brightness variation. So that was like the first recorded brightness variations of algol. Then about 100 years later, there was a proposition that the brightness variations of this star is due to some dark object coming in front of the star, or the star itself has a dark spot, and when the star rotates, that star spot comes in front, and then there is a dip in brightness. And due to this explanation, Goodrich got the Copley medal. So it's one of the earliest and the most prestigious medals given by the Royal Society. And he got the Copley medal for this idea. It would have been probably a good time to be an astronomer back then. And then another 100 years later, Pickering and Mr. Vogel, so Pickering from Harvard Observatory and Vogel from Potsdam, both of them looked at algol and took its spectra. What they found is radial velocity shifts, and that was the first time it was agreed upon that, okay, the radial velocity shifts are from two stars, so it's a binary, and one of the stars is coming in front of each other, and that's why we see the change in brightness. And to study this star, a lot of modeling and instrumentation work was advanced, because you needed to take spectra, you needed to like, not probably spectral disentangling, that came way later, but yeah, a lot of instrumentation and modeling of binary stars developed just to explain this weird star that was changing in brightness. Now, this brings us to what are eclipsing binaries in general. So it's two stars rotating about the center of mass, and when one of the star comes in front of each other, there is a dip in brightness, and when the brighter star goes behind the dimmer star, the dip in brightness is the highest, and then when the brighter star comes in front, there is a smaller dip in brightness. Now, a bit more about the Algol star itself. It's a star in the Perseus constellation. It's in the northeastern sky, and if you want to see where Algol is today, you can see it from 3:18 a.m. to 8:20 a.m. in the night. And it has a orbital period of around 2.86 days. So you can see the minima of Algol, the minima of the brightness of the Algol with the naked eye. And there is a website where you can go and see at what times the minimas will come, and yeah, the link is here, and it's just, you just need to put in today's date and it will give you a list of dates where the next minima of Algol will come. And it's visible to the naked eye, so the magnitude drops from 2.1 to 3.4, so it's like quite a high drop in magnitude, which you can see very clearly. So the next question would be much simpler one: what is a star? Anybody? I mean, I know that there are astronomers here and who are doing their graduate studies. Okay, so a star, how I define it is it is a self-gravitating object which is powered by its own, whose energy is powered by its internal nuclear fusion. So I think the two important things are nuclear fusion, which provides this energy, and it's a self-gravitating object. So its gravity is held by the energy that comes out from nuclear fusion. It typically has a core and an envelope, where in the core you generate the energy, and the envelope is supported by the energy that the core generates, and the energy is transferred from the core to the outer surface. Now, if you look at the evolution of the radius of any star, what you will find is at birth it has the smallest radius, which is at age 0, and then it slowly increases in radius and then dies as a very large radius. So the two things to take away here is that more massive ones, like the 20 times the mass of our sun here, it lives shorter and it is larger. So heavier stars are larger, which is of course expected, but then again heavier stars also live shorter. And the reason is that if you have So the reason why heavier stars live shorter would be that the faster you generate energy, the faster you burn the fuel inside the star, and then it lives shorter. Now, another thing is that the way these stars evolve, you can probably predict what a star in the middle of these 12 and 20 solar masses would do. It would be something like this. So you can easily guess what a different mass star would do if you know what two other masses of stars in between them are doing. So if the stars are single, what you can say is that the mass of the star is very fundamental to its evolution. But here in Algol, what people found was that if you look at the masses of the two stars and its radii, the less massive star in the system is a 0.7 solar mass star, which has a radius of 3.5 times the radius of the sun. But the more massive star has a 3.2 solar mass star, which has a smaller radius. So this was a direct contradiction to the then understanding of the theory of stellar evolution, that the more massive star is less evolved. So imagine the confusion back then. You are starting to develop a theory of stellar evolution, and the first binary you look at, you have good data of, contradicts all the knowledge that was there. So how do we explain such a thing, where the star is in a binary and it goes against the understanding of stellar evolution? So for that, the first thing to note is that stars don't really like to stay single. They like to live with a partner in binaries or triples, even quadruples. And since they are in close proximity of another star, they prefer to exchange matter with each other. And if you have exchange of matter, then one star can transfer some of its mass to the other star, and then you can kind of mentally figure out that, okay, less massive star can still have a high radius if you can switch around mass between the two stars. The way to do that would be take two stars and find out what we call the equipotential surfaces of the two stars. So take the gravity and the centrifugal force that can act on a point object that is rotating in the same frame of reference of the center of mass of the binary. And then you have these nice curves which we call the equipotential surfaces. And then the most important one is of this figure 8, which is called the Roche lobe. But you don't have to worry about nomenclature. So the most important thing to note is that if a point mass is to the left of that figure 8, then it's attracted more strongly by the star on the left. If a point mass is to the right of that figure 8, the point mass is attracted more strongly by the star at the right hand side. And then you let the two stars evolve. The more massive one evolves faster, increases in radius, and it fills its Roche lobe, and then it's at this point here, and then it starts to transfer mass. And then at some point you will have the masses of the two stars becoming same, because the heavier star is losing the mass and the lighter star is gaining the mass. And at some point the entire envelope of the more massive star has got transferred to the less massive one, and then you have this configuration where a less massive star is larger in radius than a more massive star. And this is what we see in the universe's algol binaries. Now, if anybody has telescopes in their backyard, you can do a lot of astronomy on these variable stars, and like not just amateur astronomy but even like professional astronomy, like checking brightness variations. Like there are some very nice handbooks on how to observe such kind of eclipsing binaries, and there are a lot of eclipsing binaries that are visible to the naked eye. All you need is like a small telescope and a DSLR. And there is also this book on observing variable stars, and it starts with like a beginner level understanding, so you don't need to even have to be an astronomer to start observing such variable stars. And yeah, I think I have 5 more minutes, so I can give a brief introduction to what Vikram is going to talk about. So what also comes in binaries are black holes, and I'm sure you have seen in the news a lot of news about gravitational wave observations, which are binary black holes merging. And in the last decade or so, we have gone from 10 detections of gravitational waves to 100 detections, and in the next few years we are going to be detecting 500 to 1,000 black holes, gravitational wave mergers. And the first results of these are something like what is the mass distribution of such black holes, what's the spin of these black holes, how fast are these black holes spinning. But again, to understand how the masses of these black holes are distributed, or how the spins of these black holes are distributed, you need to understand massive binaries, or stars that come before these black holes. And the problem is that if you start with 2 stars, put them through your favorite stereo evolution software, you would expect that you would get 2 black holes. But then the reality looks like this, where there is a lot more physics assumptions, there are a lot more knobs you can turn, and eventually what you get is like hundreds of papers predicting black hole merger rates, and which vary by orders and orders of magnitude. So it's very hard to go from here, the two stars on the main sequence, to gravitational wave mergers. And to complicate things more, you need to start with like thousands and thousands of stellar binaries to get a few handful of gravitational wave mergers. And this figure, which I don't want you to go through in detail, so this is like a way to go from stars to black holes. And you can see that there is a lot of steps that you need to take to go from two stars to two black holes. So what do we do is we take observations of stars in each of these intermediate stages, tune our models to the intermediate stages, and then go to the next step, tune our models again, taking the physics assumptions that were tuned in the earlier step, and go on like this, so that we have one set of models that can explain each of these steps instead of blindly throwing a dart that a lot of works have done, but really going into each of these intermediate steps and checking if the models can explain all these intermediate steps before we can go to the black hole mergers. Yeah, and this would be the end of my presentation, and I am sure Vikram will take over more about black holes from here.
All right, thank you so much. With that, we will break for intermission. Right now, it is 5 till 8, so we will be back here at 8:15. Go refresh your drinks, come visit us at our merch table, and we'll see you back here at 8:15. Thank you all for coming. See you in 20. Alrighty, welcome back. With that, we will begin our second talk of tonight. Where am I in here? Here to give us a look at the history and future of black holes, please welcome Steward Observatory graduate student, Vikram Manikantan.
Hey everyone. Thanks, Nick. My name is Vikram Manikantan. I'm a graduate student in the astronomy department here at the University of Arizona. And today I thought I'd give you a little rundown on the history and future of black holes, at least how us humans have interacted with them. Okay, so first of all, what is a black hole not? All right, so a black hole is not a vacuum, and it is also not a wormhole. As a kid, I really would have loved if that one was true, but it's unfortunately not the case. What a black hole really is a region in space where gravity is so strong that not even light can escape. So pictured here is maybe one of the most famous black holes in pop culture. That's Gargantua from Interstellar. If y'all have seen the movie, really hope you have if you are here. So this is a supermassive black hole. And that means, first of all, that's a black hole right there. More specifically, that's the event horizon. So the event horizon is that point of no return for even light. A little bit more about this. This is a supermassive black hole, which means it's about 100 million times more massive than our sun. Yet, it is only 4 times bigger than the distance from here to the sun. And so even though it is so much more massive, it is really not that big. And the point I wanted to make was it is extremely dense is not the right word. It's extremely strong gravitationally because it's so packed together. So I thought today we could try to figure out how we got to this point where even in pop culture we can start talking about black holes. And it took a long time to get here for us all to be sort of comfortable with the idea of a black hole. And so I can put today right there, that's us 2025, and Interstellar there in 2014. And so we're going to try to build up a little bit of history. I'm absolutely going to miss a lot of people, but that's just the nature of a 20-minute talk. I'm going to try to build a little human history of how we got to this point where we can talk about black holes in our everyday life. Or well, at least I can talk about black holes in my everyday life. Okay, so we're going to actually start with some trivia. Who do we think first came up with the idea of black holes?
Newton?
Nope, it was not Newton. This is not a trick question. The answer is on the screen. Yeah, go for it. You say Wheeler? No, not Wheeler. It was not Einstein. It was not Brunel. All right, last but not least. It was not, sorry, it was not him either. Okay. All right. Spacecraft crew, what's the rule on no one getting hands? Does anyone want to say the answer for a free, yeah, whoever said John Mitchell, sorry, someone said D over here. Yeah, there we go. He won. So it was John Mitchell. I'm actually so glad this turned out that way. Yes, it was John Mitchell, a very lesser known scientist of the 1700s. And so that was the point of this talk. I didn't realize he was the person who first thought of the idea of black holes. But do not worry, we're going to hear about all of these scientists, and I'm actually going to place them on our timeline with Interstellar. Okay, so Brahmagupta. He's first in 628. There are no photos of him, obviously. But he's the first person who described gravity as an attractive force, meaning that 2 objects of mass would actually attract each other. He did a bunch of other things. Geometric stuff. He did a lot of geometry. He was the first person to use 0 as a number, which is actually a big moment. And he was also the first person I know to throw shade at other astronomers. So I read this about the story where apparently once he'd done all his work, he wrote a text about it, as you do back then. And in the first 11 chapters, in every single chapter, he criticized other people. And then in the 12th chapter, he spent the whole time criticizing other people. And so you can say he's a bit of a hero of mine. But to be fair, he could only do that because he was correct. He pushed back on the idea that the sun was closer than the moon. Turns out to be correct. So that's why he could do that. Okay, so next up we have Newton. So you'll notice I jumped forward like 1,000 years. A lot happened in that time as well. But if we're to get straight to the point, he's the first to describe gravitation as a universal force, meaning that it affects and applies to all bodies in our universe. And this helped him explain the elliptical orbits in our solar system. Up until that point, do we do choo-choo for this? Yeah.
Let's go.
Oh, it's coming, it's coming, it's coming. Not yet, all right, thank you. Okay, so he first explained elliptical orbits. So there were planetary orbits that were a little bit elliptical, not quite circular. Here it comes. Okay, so it was really this that confirmed his theory of gravity as the one that seemed to apply at the time. And he also did a bunch of other stuff, invented calculus, just as you do. Okay, next up we're into John Mitchell, or Michel. I'm actually not sure how to say that. So he was the first person to describe a black hole. So if we back up a second, he was actually a philosopher, as many scientists were that day. He kind of just studied everything. And a clergyman, which means he was like part of the religious. Sorry, I'm not religious, so I that's all I know. Okay, so he first proposed the idea of black holes. So he took the sun and he said, if the sun was 500 times bigger, what would happen? And it turns out, right, he found out that if it was 500 times bigger, the force of gravity on the surface of the sun would be enough to keep light in. And so you would not see anything, because no light would be leaving this proposed star. And then, not just that, he then predicted how we could find them, and was correct. And so what he said was, if this star happened to exist, or this not star happened to exist around another star, we would see it through its gravitational effects. And when we get to 1971, we will actually see that he was correct. Okay, big dog. Einstein. So everyone's heard about Einstein. So he came up with the theory of general relativity. And what his theory said was, gravity is not a force, but rather it is a manifestation of space-time itself having curvature. And so if we take this image and maybe the analogy of someone sitting on a trampoline, if you have mass, you will curve the space-time around you. Just like if you're sitting on a trampoline, you will curve the trampoline around you. And because of that, objects will fall towards you. And so then he came up with this famous equation. This is the only equation. And this equation basically says that here, mass tells space how to curve, and eventually space will tell mass how to move. And so it looks like a very simple equation. It's super ugly. So this is my research. When you get into the weeds of it, it is pretty terrifying. But at the surface level, it really describes elegantly how our universe works. Okay, all right, so this is where we get a bit finicky. So Schwarzschild, let me back up a second actually. So I just said this equation is really ugly. You would imagine it takes a long time for someone to like figure out a solution to it. 1915, 1 year later, Schwarzschild said he has a solution to Einstein's equations. And it's still a solution that we use today. So he did a pretty good job. And the solution that he came up with was one around a spherical body. And so by spherical body, I mean something like our sun or our Earth. And his solution to Einstein's equation really predicted very well how things might move around spherical objects like our sun. Finkelstein, like 40-ish years later, realized that there was a quirk to Schwarzschild's solution, and that there was a specific radius at which not even light could escape. And that sounds really familiar to us. That is the event horizon that John Mitchell, almost 150 years ago, also predicted. And so I've got this diagram here. You can see space is described by this grid, and the fact that it goes down in a hole is like where your black hole is. And they've drawn with this yellow circle the point at which light, not even light, can return out of this well. Okay, and so up until this point, we've really developed the idea and the theory behind what black holes are. But we haven't really gotten much closer to figuring out where they are or where they exist. And so the natural question to ask is, what sort of object is dense enough or massive enough to actually create this event horizon? And so I'm about to skip forward a few years, but there's a lot of people I should mention on the way. So there's Chandrasekhar, who developed the idea of the white dwarf, and the first compact object, which is a white dwarf that is maybe the endpoint of our sun, or will be the endpoint of our sun. Astronomers looking at me. But then there's another object called a neutron star, which is even more dense than a white dwarf. And that's just one step away from a black hole. And so that's where Jocelyn Bell comes in. So Jocelyn Bell Burnell was a graduate student when she discovered the first neutron star. It was not just any neutron star. It was what we called a pulsar, which is a neutron star that's rotating fast enough. It's rotating and also has like poles with magnetic fields. And anyways, we see that these poles shoot past Earth as the star rotates, and we see these flares of light. And these flares are extremely consistent. And so it was almost by accident that Jocelyn Bell Burnell found neutron stars or pulsars, but it was definitely her hard work that identified them. And for a little context, the neutron star is so dense that a teaspoon of its material would weigh 10 trillion pounds. I don't really have a concept for 10 trillion pounds. I don't really know what that means. So I thought I'd put some funner context to it. All right, that's a neutron star. This is not the fun context here. This is a neutron star hovering over Vancouver, I think. And so that's a similar mass to our sun, yet it's the size of a city. So you can imagine maybe how dense it is. I actually looked over to my cat at that time, and I was like, I wonder how much you would weigh if you were made out of neutron star stuff. And it turns out the cat would weigh almost as much as one of Mars's moons, Phobos. And so this is definitely a fever dream I've had at some point. But that's how massive that cat would be. Okay, and so in that same year, in 1967, there's Jocelyn down there, we had the first use of the phrase black hole. And so I promised I would get to John Wheeler. This is John Wheeler here. A student of his, in his lecture, suggested the phrase black hole. And so while a lot of credit goes to him, it should also go to the student, who remains unnamed. I don't know who it is. And he continued to use it because it was catchy and it was really easy to say. And he was totally right. People love the word black hole. I also wanted to give a honorable mention to the textbook he wrote. It is by far the heaviest textbook I've ever held in my life. It's just massive. I got sent a PDF. I got sent a PDF of it, and it was like half a gigabyte. It's just like it had no right being that big. Sorry. Oh yes, it could be. It could be. So I didn't see where that was coming from. Oh, there we go. Hey, Osler. Okay, and so in 1971, about 4 years later, we had the first black hole detection. So it was found by multiple scientists at the same time, so I didn't want to give credit to any one of them. But what happened was they launched an X-ray mission up into space, and they found a really large amount of X-ray emission, so the stuff that people look at your bones with. And they found it from a very small region. And the only explanation at the time could be that it was coming from one of these black holes. And the other way that we found it was that it had a companion star. But we could see the star, but we couldn't see the star's companion, which was a black hole. And the only explanation for the motion of the star was that it had a dark companion. And so Mitchell, 150 years ago, turned out to be right. Okay, all right. Sorry, I forgot how I was going to lead into the next one. And so this is awesome. This is really cool. Cygnus X1, I think, is still one of the most famous sources. I'm looking over at Koushik because we study stuff like X-ray binaries. Still one of the most studied sources, right, in our field. But astrophysicists and very specifically people who study gravity wanted maybe a little more concrete evidence that Einstein's theory of gravity was correct. And so it's really hard to do astronomy. It's really even much harder to do astronomy when your objects are invisible, like black holes. And so you can see the problem that people were running into. It turns out Einstein's theory had a really natural way of fixing this for us, and that was the prediction of gravitational waves. And so this prediction said that compact objects, or any object, if it was accelerating, would produce ripples in space-time. So these are like the ripples you would see if you're moving through a pond. Except these ripples would be tiny. I'm going to flash the number up. It's 1 part in 10 to the 20. Again, I don't know what 10 to the 20 means, so I thought I'd do a little bit of playing around with some numbers. And that's like measuring the distance from the Earth to the Sun and having it change by 1,000th the width of a human hair. So that's the sort of change in space that we have to measure to actually see these gravitational waves. And you'll probably think, who's crazy enough to do it? NSF were crazy enough to do it. And so in 1992, they being Congress, funded LIGO, which is the Laser Interferometer Gravitational Wave Observatory. And the idea here was you would send lasers off in opposite directions, or perpendicular directions, and they would hit a mirror and they would come back. And if nothing happened in the time that they went to the mirror and got back, then you'd know that nothing happened to space. But if they got back and something was a little funky, a little off, you could maybe say that, wow, maybe space itself was contracting at that point. Specifically, if there was destructive interference when the light beams or laser beams got back to us at our detector, we could actually predict a contraction or an expansion in space-time itself. So we had lasers measuring how space-time was changing. But for 20 years, they had no results. They had no results at all. And before we get to the result, I wanted to flash this quote here. This is from the NSF director at the time. It says, "The National Science Foundation is the agency that takes these kinds of risks. We support fundamental science and engineering at a point in the road to discovery where that path is anything but clear. We fund trailblazers. It's why the US continues to be a global leader in advancing knowledge." I hope that remains true. I just want to say that. And she was right. Choo-choo. So after 23 years, both LIGO sites, that's one in Hanford, Washington, and Livingston, Louisiana, pretty sure, they both detected the same gravitational wave merger event. And so we saw these two black holes that were orbiting each other, creating these ripples in space-time, and 1.3 billion light years away, we measured these oscillations in the space-time from our lasers, and that was huge for us. I had a feeling that NSF were like about to give up. At least those are the stories I've heard. And so hopefully this video works. Yeah. Okay. Awesome. So this is a simulation of that merger. So what you're looking at are the two black holes that are obviously dark black, and you're looking at the space around them that's being warped, and that's the light passing through the black hole, through the binary black hole spacetime. And eventually, they're going to come together and merge into one. That was slowed down a lot. I should make that very clear. And now we have over 290 detections of these binary black holes. So after 23 years, nothing, and in the last 10 years, we've had over 290 detections. But it doesn't end there. The future of gravitational waves is extremely bright. So this is the only graph I have on here, I promise. we have time here, our human years, and the number of detections here on our y-axis. You'll notice in 2015, that was the first detection. It was slim pickings for a while, and then it picked up. Each one of these vertical bars are what we call observing runs. And so O1 is observing run 1, O2, O3, O4, and we're actually now getting to the end of O4. And this prediction, plot by floor, was actually almost spot on. We got to about 300 detections. O5 will bring another few hundred, up to 1,000. And then we're looking here at future generations of gravitational wave detectors. So that's A-sharp, which is an advanced version of the laser interferometer we just had, and the Cosmic Explorer. And so we're about to have, in the next 15, 20 years, hundreds of thousands of these detections. And so that's going to completely revolutionize the way we study these systems. Okay, nice. So that was actually not the only way we can find black holes. In 2017, the Event Horizon Telescope, many of whom are here at the University of Arizona, helped create these images here of two supermassive black holes at the center of M87 and our own galaxy called Sagittarius A star. So what they did was put together a network of radio telescopes. They used interferometry, there's that word again, and they produced these images of the stuff around black holes and the event horizon shadow itself. And so this was the first direct image that we could do of supermassive black holes. So what's next? We've come a long way, right? We've come a long way in about 1,000 years. In the last 10 years itself, we've done a huge amount of science. So we're going to put more lasers on Earth. So that's the first thing. So I mentioned the Cosmic Explorer, which is going to detect almost 100,000 of these binary black hole mergers every year. But not just that. It's going to observe every single stellar compact object merger, so stuff around the mass of our sun, in the visible universe. So we're going to have a complete history of how our universe has evolved and how the stellar objects in our universe has evolved. And then we're actually going to take it one step further. We're going to put lasers in space. And so we have the Laser Interferometer Space Antenna planned to launch in 2035. And this will actually put 3 spacecraft with lasers on them in space to orbit behind the Earth. And the distance between those detectors is about 2.5 million kilometers. And they're going to help detect binary stars in our galaxy. So binaries like the ones that Koushik mentioned, including white dwarf binaries, and also the merger of supermassive black holes. And so that's bridging the gap between the supermassive black holes that the Event Horizon Telescope observed and gravitational waves from those events. And so there are people working on this right now, preparing for this mission. One of them is me. And so I help try to build some of the theory behind what we might expect these supermassive black hole mergers to look like. And I figured I was going to run out of time, which I almost have. And so I'm going to leave it right there. But I am happy to take any questions about black holes. It's a great question. From what I
repeat it for the screen?
Oh yes. Why did it take so long to detect the first gravitational waves? So from what I understand is that they needed higher sensitivity. So the first 20 years or so, they were working with a sensitivity that was about the 1 part in 10 to the 20 that I mentioned, like the width of a human hair from here to the sun. But it was upgrades that they built in like 2012, 2013, around then, that really pushed it into the ability to observe these events. And there's also a little bit of serendipity. That event happened right as they turned on for that first observing run, and so they got really lucky, because it could have been another few years or so before they saw an event that was loud enough to observe. So technology, I think, is the short answer. Yeah, I can tell you a bit about pulsar timing arrays. I feel like the person is in the crowd who could tell you more, but yeah, so pulsars are neutron stars that are rotating very fast. And every time they rotate, they flash light at us. And they do this at a very consistent, with very consistent timing. And so if we see a pulsar and we observe it, we should be able to predict for, on human timescales, exactly when that pulse is going to reach us. Now we can put together an array of, in this case, 67 pulsars, and we should be able to predict exactly when each pulse reaches us. However, if we detect a delay in a set of pulses coming from a certain region in the sky, we could maybe make the claim that the space-time between us and those pulsars is being squeezed or stretched somehow. And so that delay in the pulses actually tells us if there's a gravitational wave passing between us and those pulsars. So it's a timing array, yeah. Yes. Actually, let's go on the front first. Yeah, go for it. Sorry, what was the current theory for? Oh, so it depends on the size of the black hole. Oh, yes, thank you. What's the current theory and what happens to you as you fall into a black hole? So it depends on the size of the black hole. The reason it depends is you want to think about the force on your head versus your toes. And so if you're going towards a black hole that's really small, let's say the size of my fist, the force between the part of me that's closer to the black hole and the part of me that's further away is really different. Just as if the force when you get close to the sun is much stronger than the force on Earth. And so if the force is really different from you at your head to your toes, you're going to get pulled apart. That's called spaghettification. However, that's the scientific term for it. I'm being serious. However, if it's a supermassive black hole like Gargantua, you're kind of like a speck compared to that black hole. So the difference between your toes and your heads is not really important, and so you will just fall in. And it will seem like you've fallen very slowly to everyone else, but to you, you just fall in like it's any other day. Obviously, it will be your last day, but depending on how long it takes for you to fall in. Sorry, in the back. Oh, that's such a good question. So how do you tell what direction the gravitational waves are coming from? So I want to say triangulation. So if you have many detectors on at once, then you can figure out where in the sky it's coming from based on like arrival times, but also like what we call like gravitational wave polarization. Yes. But the dirty little secret to that is it's really hard, and we're still quite bad at it. And so if you go to these open catalogs that contain all these gravitational wave events that we've seen, they'll put on there what's a sky map. And so that's like, if you look up, that's the sky, and they'll give you these confidence intervals for where these gravitational waves are coming from. And they will be like, sometimes they'll just be like half the sky. Like they think it's like somewhere over there. And so depending on what kind of event it is, you can use our electromagnetic telescopes, so normal light, to try to follow up these events. So if you see a gravitational wave event, but you kind of don't know where it is, if you see a flash of light in that general direction, you can maybe put them together and see if that's the same event. Yeah.
Why can't they be wormholes?
Sorry?
Why can't they be wormholes?
I mean, I think I answered I don't know.
Don't kill my dreams.
Yeah, my dreams too. So the question was, why can't they be wormholes? The honest answer is I don't know. Yeah, I mean, I've seen some. I'm going to say a crazy thing. I've seen some wormhole solutions. It's something we use in our research actually sometimes. And I think maybe it's the idea that in a wormhole you want to be able to come out the other side, and if it was a black hole, you just wouldn't be able to come out the other side. But don't quote me on that. Oh, okay. All right. So let's say I shoot a laser to Nick and back, and let's say there's 10 meters between us. Okay. And I know the light in my laser has a wavelength of 1 meter. All right. So there's gonna be 10 wavelengths between me and Nick. But if a gravitational wave passes through and the space between me and Nick squeezes, like physically, then it's not going to be 10 wavelengths anymore. It's going to be like 9.5. And so when it arrives back to the detector, the light that went the other way and came back, which wouldn't have been affected because they're perpendicular, it will destructively move here, because you'll reach a peak with a trough, and those will cancel out, and so your path length changes. Yes. So I didn't bring my comedy self for today.
All right, thank you so much, Vikram. That will do it for tonight's spacecraft number 107. So, regarding next month, we do expect probably to be here at Borderlands, but since Borderlands' future here downtown is in flux currently, please stay tuned to our social medias and to our email list if you are on it. Just keep an eye on things, just in case things change. That goes for pretty much the whole summer. Our next show, as we anticipate, will be on June 17th. So mark your calendars for that day. That will be Space Drafts number 108. Our trivia winner over here, who got in on the last option, please come and visit us over here for your free piece of merch. And that's all. Thank you all for coming once again. Our next show will be June 17th. See you all then.